physics talk. My name is Evan Dalaku. I'm a third-year engineering physics student, and today I have the pleasure of introducing Dr. Patricia Burchat. Dr. Burchat's research is spanned from the tiniest scale, with studies of fundamental particles, to the largest, which works on observational cosmology. She said in a 2008 TED Talk that these two aspects of physics are closely related, and she's in a great position to make such a claim. Dr. Burchat has worked on multiple particle physics experiments at the Stanford Linear Collider and Fermi Labs, studying weak interactions in these fundamental particles. She is currently working as a part of the large Synoptic survey telescope dark energy science collaboration to uncover the secrets of dark energy. Before this, Dr. Burchat obtained her bachelor's in applied science in Einstein and then her PhD at Stanford. The multiple awards she has won include the Walter J. Gore and Judith Poole Award for her excellence as a professor and mentor while she was teaching at Stanford. She's also taken part in designing Stanford's engineering science physics program and has worked to make the university's majors more accessible to incoming students. Please join me in welcoming Dr. Burchat.
Thank you. Okay. Thank you. There we go. Okay, so it is an honor and a privilege to be here and to be invited to give this lecture. And I'm going to tell you a little bit about the research that I do, but I'm going to tell you quite a bit too about the pathway that I took from engineering science here at University of Toronto, even before that, to where I am now. And my theme is going to be advancing our understanding of the universe through team science and engineering. Okay? That working in teams has become more and more important, and I think a lot of your coursework may be already reflecting that. So just as an example, if we look at the role of team science in recent physics Nobel Prizes, in 2017, the Nobel Prize in Physics was given for the detection of gravitational waves. And that was with this experiment called LIGO, right, which are these 4-kilometer L-shaped lasers that interfere. And they were measuring the fact that space over 4 kilometers was changing in terms of its length by 1/1000th of the diameter of a proton. Okay, over 4 kilometers. And you think that is just impossible. But it was a science and engineering feat, okay, conducted by a whole group of engineers and scientists. Okay, and people coming from engineering science are perfect for that kind of thing. And so down below, those are just the icons related to the universities represented by the collaboration. So it was over 1,000 people to make that happen. And then if we go back 4 years earlier, that's when the Nobel Prize was given for the discovery of the Higgs boson, which is an interesting particle because I'd say probably billions of people on this planet have heard of the Higgs boson, but almost none of them would be able to explain what it is, right? But they know it was significant to discover it. And that was basically co-discovery by the ATLAS and CMS experiments, 2 different experiments at CERN at the Large Hadron Collider. And each of those collaborations is about 3,000 to 4,000 people. Okay, a majority of whom are graduate students and postdocs, so very young people working on these experiments. So you see these super big collaborations winning Nobel Prizes. And then in between, so it's starting to look as if there's a pattern with the Nobel Prizes, that in odd years it goes to team science, okay? So I'll put my glasses on for this one. So 2015, it was for the discovery of neutrino oscillations. And that was like hundreds of people in a collaboration, so relatively small on the scale of these other ones. And in 2011, it was something that is related to the theme of my talk, and that is the discovery of the accelerating expansion of the universe, is what they wrote. I'm going to emphasize that it's really the accelerating expansion of space, okay? And something that we don't know why it's happening, so we label our ignorance with something called dark energy. So that'll be, we're coming back to that. So it looks like maybe 2019 will be another team science. And 2018, you probably are all quite aware of the Nobel Prize in Physics, right, for the very, very short laser pulses. And actually a week ago, I was at the conference, the Canadian Conference for Undergraduate Women in Physics in Ottawa, where there are a lot of engineering physics students there too. And the keynote address at dinner was by your own female Nobel laureate, right? Only the 3rd female Nobel laureate ever. And she gave a wonderful, humorous talk after the dinner, Donna Strickland. Okay, so a little bit about my journey to exploring dark energy. And we're going to come back to this image later because it's very much like what we actually explore with imaging. This is imaging by NASA looking down at the part of the North American continent. And so where I started was that I grew up, if we look up here, try to find Toronto over here, and then up here toward, that must be Montreal and Ottawa, and then find a really dark patch right around there. And that's where I grew up, okay? And it's a little town called Barry's Bay. It's about 4 hours north of here. I used to take the bus down to University of Toronto when I would come to school. And this is me and two of my sisters. That's me and my older sister and a younger sister and my dad. And he had a grade 7 education, okay? But he was obsessed with building airplanes. And these are wood frames of wings that he was building, so full-scale airplanes. And ironically, when I was in engineering science, I wasn't that interested in the aero option, but one of my kids is obsessed with building airplanes and has a startup developing autonomous electric airplanes now. So I see my dad come through in this kid, okay? So this picture, two of my siblings and myself, my dad, and I had 8 siblings altogether. So there were a lot of kids in the family. And because of, in 1967, Pierre Trudeau, the father of your current prime minister, one of the things he did for centennial year in Canada was build high schools in remote areas that had no high school before. And so the high school was built in my town when I was 9 years old, so that I could go to high school and then go to University of Toronto and then end up as a professor, okay? So that was a great thing to do for a centennial year. So after this then, going to that high school, I looked at different majors and spotted engineering science and thought that is the perfect major. I can defer my decision as to what type of engineering for 2 years because I really didn't know, really what is chemical or mechanical or electrical. And in the meantime, for those 2 years, you do an in-depth first principles understanding of all this stuff of math and science, just the perfect match. And if I had to do it all over, I would do engineering science again. Even ending up as an experimental physicist, it was great training. So then I had to choose my option. Oh, tough decision. So I was thinking, well, maybe chemical engineering. I had a really good chemical systems professor. Now, the chemical option doesn't exist anymore, right? Okay, so it's okay that I can say that. I did one summer working at Shell Oil, and I thought, oh my God, I do not want to be a chemical engineer. And so I arrived back at the beginning of 3rd year and started looking at the options again. What should I take? And there was this nuclear and thermal power option. And one of the other speakers also did that, the one talking about energy and solar and stuff. So he did that one as well, and it's obviously no longer offered. But one of the first things that I had to do was take a nuclear physics class. And the professor's retired now, and it was fantastic. And I realized I loved understanding things at a really fundamental level. And so after working with him, or taking this course for a semester, at the end of it, he said, would you like to do research with me? And back then, so that was in 1979 or 80, so a long time ago, 40 years ago? Yeah. And it was much more unusual back then to do summer research, actually. And I didn't even know what summer research was, but I said, sure, sounds great. And it was at the Chalk River Nuclear Laboratories in Deep River, which was about 60 miles as the crow flies from where I grew up, actually. But I'd never been there. So I went there and discovered that experimental particle physics, or experimental physics, is like solving puzzles that no one else has solved before. And I don't actually like doing puzzles where a lot of people have solved it, but these kinds of puzzles, I thought, wow, you can be a physicist and solve these puzzles. So I think that's what I want to do. So the next semester, after taking nuclear physics in the fall, then I thought, well, that was great. Let's get even smaller and go down to particle physics. So I took an introduction to particle physics, mind-blowing. I thought, whoa, all these quarks and leptons, you can really make sense of what makes up the universe and matter. So then, and that professor said, do you want to do summer research with me? But I'd already obligated for nuclear. And I said, how about the next summer? So after 4th year, so during the 4th year, I decided to apply to grad school for PhD programs. And in the United States, and so I just consulted with my professors, especially some of them who had gone to graduate school in the US. And they explained to me that in the US, you don't have master's programs in physics. You apply straight to a PhD program. And I said, great, so where should I apply? And they just gave me a list of names, and the names meant nothing to me, okay? And so I just said, okay, got it, apply. And then once I got in, I was thinking, well, where should I go? And I chose Stanford University because of the accelerator. So I made a journey across the country to Stanford over here. You know, never been, had been out of Ontario once, okay, but just kind of went there. And on the way, actually, I stopped at Fermilab for the summer right here to do research with the professor who I took particle physics from. And one thing about you know, going from a semester system like Toronto to a quarter system like Stanford, you end early at Toronto, like in May, and you don't start till the end of September at Stanford. So it was like having, I think it was like almost a 20-week summer, or 16 weeks or something like that. So I put 2 8-week summers together and did a bicycle trip for 8 weeks in Europe and worked for 8 weeks at Fermilab. So that was a really good thing. Now you have the option now of doing a whole year of something else, I know, in between 3rd and 4th year. I think it's really good to do that and get opportunity to do something else. So I went to Stanford, and I chose it basically because of this accelerator. In this picture here, actually the Pacific Ocean is off beyond those hills, and then this is the 2-mile-long accelerator point going from west to east. This is actually a highway here going from San Jose up to San Francisco. And 2-mile-long accelerator, and it was still doing particle physics when I was there. Now it's primarily used for something called photon science. They use it to produce it's called a free electron laser. So it's an X-ray laser beam with incredibly short, incredibly intense pulses for mostly doing material science and biology and studying proteins and things like that. But SLAC also hosts now construction projects that cannot be done at a university. They're just too big. And so I'm involved with one of those. So I'll get to that now, I think. Yeah. So after working in particle physics for a few decades, maybe 2.5 or 3 decades, I got to the point where I wasn't on a learning curve anymore. I felt like I kind of knew what we were doing. It was very predictable, and I was not feeling excited about it. And I thought, you know what, I want to be a student again, basically, okay? And I have tenure as a professor, so I'm going to switch fields, okay? And it was relatively easy to switch because I wanted to go to exploring not the ordinary matter in the universe, so that would be like nuclear physics, or the stuff that we produce at accelerators, which is very exotic particles like quarks and stuff, but they decay to the ordinary matter very quickly. But around that time, it was becoming clear that about 95% of what makes up the universe is in the form of stuff that we label dark matter and dark energy. That's hidden over here, this big slice of the pie right here. And that's me giving a talk to high school students. Someone take a picture, and I thought, oh, that's kind of nice, though. So dark matter and dark energy, we don't understand what it is. And dark matter, there's some exploration going on with laboratory-type experiments, but a lot of it is being done astrophysically, like looking out into the universe to try to learn about the dark matter and the dark energy and what it might be. And so that's what I decided I would like to turn my attention to. So like I bring out an introduction to modern cosmology by Barbara Ryden, if you're interested in like getting up that learning curve fast, really good book. Do you use textbooks by David Griffiths? Yeah, so great textbook writer. And Barbara Ryden is kind of like David Griffiths for cosmology, so that's very good. So start to learn all that, and then get involved with something called the Large Synoptic Survey Telescope, okay? So this is something that people have been dreaming about for literally about 3 decades. And any big project like this, you go through various phases. Design, and then review, and then review, and review, and review, and review, okay? And not enough funding for it. And so eventually, the funding came through, okay? So construction started about 3 or 4 years ago, or maybe 5, something like that. And we're well into construction now. I'll show you some pictures of that. And we'll start getting first light pretty soon. And I'll describe the name for you in a minute and where it is, et cetera. But just for scale, this is a picture of me to scale. I'm not standing on the telescope, obviously, but I am actually standing on the telescope site up in Chile. So first of all, this is an artist's rendition of the telescope dome and support building. This is a 3 or 4 story support building right here. And this is a real picture of the mountaintop in Chile, okay, where this is. And so geographically, here's the coast of South America right here. And Chile is this very long, thin country. And right now, once LSST comes online, about 70% of all the optical observing on this planet will be done in Chile. Okay? And it's both because they have really good laminar flow of air, okay, that's coming off the ocean and then just rising in a very nice laminar way, not turbulent, so that we can get good seeing, as we call it, when we're looking through the atmosphere. And they've got very high and dry. So we're down here, but you might have heard of the Atacama Desert, and there's some telescopes at 14,000 feet. That's in this region. You can tell it's dry. Look how brown it is. There's no vegetation there. Okay? We're only at 9,000 feet, so about 3,000, almost 3,000 meters. Okay? So 9,000 feet, you can operate. Your cognitive abilities are okay. Okay? 14,000 feet, they have to put oxygen in the buildings, actually feed in, and to pressurize them so that people can just even think at that altitude. So in terms of time scale, first light, we're going to have the whole telescope will be there, and we'll have a small commissioning camera. Small, about this big in area, the sensors, okay, compared to like in your phone, it's like a millimeter by millimeter or something. So about that big. And then the final camera will go in and be ready for operations after a commissioning period. First Science Light 2022. So good timing for you, okay, in terms of that we'll start to get stuff. But you can still be involved in the commissioning, which is a blast, okay? And in fact, for your one-year terms, if anyone was interested in this, talk to me afterwards about LSST is hiring, okay? And we, in fact, for things like commissioning, we need people who could come in for a year and work, because commissioning is over after a while, okay? Okay, so that's kind of the time scale. So now for some real pictures. So this was in 2015, April, so almost 4 years ago, when the construction started. And in Chile, for these telescopes, they have a ceremony called laying of the first stone, or in Spanish, primera piedra, which apparently means that. This is me. This looks tiny. This is actually a giant construction vehicle back there. I don't know, something about the perspective. It looks small. As this is a big hole here that they were drilling down to where the telescope will be mounted into the bedrock. And they erected this big tent that's just down the slope there. There's the ceremonial first stone. There's me. And these telescopes are so important in Chile that when you do the first stone, the Chilean president, Michelle Bachelet at the time, she's now the head of United Nations Commission for Women. She was the inaugural lead of that. So you might hear her name in the news, Michelle Bachelet. And then director of the National Science Foundation, France Cordova, who actually happened to go to Stanford as an undergraduate, and she majored in English. Okay, and then she went down to Southern California and got a job at an observatory, like just doing work at this observatory with her English major. And she loved it so much, she went back to school, got a master's in physics, and then a PhD in astrophysics. And she's a top astrophysicist. She has this whole career as an astrophysicist before becoming director of the National Science Foundation, which is one of the top funding agencies in the United States for science. So she was there too. So it was a great, fun event. So this is a picture taken about 10 months ago, so March 2018. So it's trying to look like the artist's rendition, okay, with the construction, the support building here. You can see cars here to get a sense of scale. This is where the telescope will be right here. And I went on the web. There's 3 webcams on this if you just Google LSST webcams. And so this was a picture that I just grabbed last night. So January 24th, and that's what it looks like now, okay, from one of the cameras. So you can see the whole support structure coming up here for where the telescope will be. Okay, so why are we building this telescope? And as you may know, there are a lot of telescopes in the world. So what's special about this one? One of them is the breadth of science that it can do. So we have 4 what we call science drivers. These are the things that drove all of the engineering specifications and the requirements for the telescope, okay? So as you know, or you will be learning in your classes, setting requirements and specifications is really important and a real skill. So one of them is taking an inventory of the solar system. So that's just stuff nearby. And when we look at this, you might say, is that a picture of the solar system? So there's this like donut here. Do you know what that is? What's in that donut? Yeah, the asteroid belt. Yeah, so those are all asteroids there. So one of the things we'll be doing is near-Earth asteroid detection, okay? This was actually initially not really part of the plan, but Congress in the United States had a mandate, or they did a mandate that we must find, we, meaning human beings or something, find all asteroids down to a certain size that could possibly come within a certain distance of the Earth, but it was an unfunded mandate. But then people noticed that, oh, this telescope is probably going to be able to do this for us and get a lot of those asteroids. So that's one thing. Another is exploring things that change in time. So we're going to be taking 30-second exposures and just keep doing it and doing it and doing it for 10 years. So we'll be able to monitor things that change over between actually 2 15-second exposures, or over a day, or over a week, years, things like this. And that could be things like the center of galaxies are highly changing with time as black holes are forming or undergoing different things, okay? And so there's a lot, or supernova going off, things like that. Then mapping our own galaxy, the Milky Way. So by measuring all the stars and how they are, the parallax of the stars, et cetera, and just basically measuring where are all the stars and figure out more about our own Milky Way and learn about the dark matter distribution in our Milky Way. So talk a little bit about that. And then finally, the cosmology part, okay? And this is the part that motivates me. So probing dark energy and dark matter. So what makes up this 25 plus 70% of the energy density of the universe, okay? So I'll come back to that later. So this is one example of, I mentioned at the beginning, team science, okay? That you look at all this stuff here, there is almost no one in the world who has deep expertise in all of these ways to go far, okay? So therefore, the only way to go far is to go together, okay, in a team. Okay, let's see. Oh yeah, so the Large Synoptic Survey Telescope. So let's talk about the name for just a minute. Okay, terrible name. Nobody knows what synoptic means. And we're actually going to rename it at some point relatively soon, or at least part of it, to commemorate one of the donors who got the telescopes funded in the beginning. And actually, I should mention, private donors was very important in the beginning to get some long lead items going, do all these designs, et cetera, go through all the review process. But now it's the National Science Foundation and the Department of Energy that are funding it. But once it's built, then we get into operations. And operations will be about $60 million a year. And we were asked, the LSST Corporation, which I'm a member of the board, we were asked to go around and find international contributors who would be interested in contributing to the operations of the telescope and therefore get data and access to the data. And so Canada is a contributor, and there's a consortium of universities led by University of Toronto, and also Waterloo, UBC, Western, et cetera. Okay, so Canada is involved in this experiment and will be involved in the operations. Okay. Okay. Oh yeah, so synoptic. This is the part. Large, we know. Survey, because we're doing a census of the universe. It's that kind of survey, so a census. And then synoptic. So the dictionary definition, affording a general view of a whole, or manifesting or characterized by comprehensiveness or breadth of view. Good, we would like that, okay, to be comprehensive and a broad view. So it's actually a pretty good name for it, if we knew what it was. Now, LSST, Large Synoptic Survey Telescope, but you look at this telescope, and it doesn't look anything like a classic, long telescope that one would look through. It looks very short and stout. So LSST could also be the large, short, and stout telescope like this, okay? So compared to the kind of stereotypical telescope like this. So let me explain why it's so short and stout. If we took away all of the mechanical structures and only left the optics and the camera, okay, the part that we really care about and we wish that we could just hang in midair, it would look like that, okay? So mirror down here, and this is the primary mirror. It's the mirror that the light hits first, and it's annular in shape, okay? Ignore the part in the middle for now. And so basically, all the light coming down in a donut, okay, will hit that annulus. So, and then will be reflected, and this is concave. And then it comes up to here to a convex mirror, actually. And then from there down to, so this is the primary, secondary, down to the tertiary mirror, which is cut out of the same piece of glass as this, which is really unusual. Okay? And then from here goes up through the lenses. Okay, there's some final corrector lenses and a filter. so that we're only seeing certain bands of the optical spectrum. And the other filters are tucked over here. This is a mechanical feat, okay, to have this filter exchange mechanisms that can bring these filters down and pop them in without taking basically any room, because you don't want to block the light that has bounced off here and is going to come down here, okay? So an engineering feat to build this camera. Right, so that's what's there. And in terms of how big is that, it is the size of a Volkswagen bus, okay? That is the camera. And it is right now being assembled in a clean room at SLAC, the National Accelerator Laboratory near Stanford, okay? So the camera is there. And that's another thing, you know, lots of room for working on the camera. And it's like being integrated together now, lots of integration and testing to make sure that it's going to satisfy the specifications that we need. Okay, so that's the, what the telescope looks like. Now, I still haven't really answered at all what's special about it beyond somehow broad or whatever. So this was put together a few years ago, and it is the family of current and possible future telescopes. And for scale, here is a tennis court and, is that a basketball court? Okay, good. So tennis and basketball, oh yeah, it says down there, basketball court. And for scale, okay? And your eyes are kind of drawn to these three behemoths here, okay? Those are possible future. Actually, the European one is under construction. 30 meter, they're trying to get it going on Mauna Kea, and there's a lot of resistance to building by the native peoples of Hawaii to build more telescopes on Hawaii. So that's a bit stalled. And then there's this one is under construction right here. And then the space telescopes, the one that are up in space, Gaia, Kepler, and the Hubble Space Telescope, that's them, okay, their area. It's really hard to put stuff up in space. That's why we're down on the ground, okay, so we can have a bigger one. And I noticed that this one is in British Columbia. It was Large Zenith Telescope. Does anyone know what that mirror is made of? Does anyone know? Yeah?
Is it made of mercury?
Yes, spinning mercury. Okay, and I was watching a video of it this morning, actually, because I thought, really? Yeah. And right, they spin it, and there's like this blob of mercury in the middle, and as they're spinning it up, and there's someone there actually like spinning it, like getting it going faster and faster, watching the mercury blob spread out until it gets right to the edge, okay? But it was an experimental one. The site in British Columbia, it was like high, but the seeing, that means the turbulence through the atmosphere is not good enough to do astronomical quality imaging, so it's more of an experimental thing, okay? But anyway, that's for scale. So then you kind of look at that and like, well then where is the LSST, the Large Synoptic Survey Telescope? It's certainly not standing out, and it is this one in the middle right here, okay? And it's the annular shape, and I think that hole in the middle is actually a little bit too big. But anyway, the size of this mirror is, across the whole diameter, is 8.4 meters, okay? So you kind of look like 8.4 meters. It's about the width of this hall, okay? So roughly the size of this room is about how big that mirror is. And that's quite large. In fact, it's for a monolithic, you know, glass, like as opposed to these segmented mirrors. It's one of the biggest ones, okay? And the reason it's 8.4 meters is because it's made at the University of Arizona in one of the best mirror-making facilities in the world, under the stadium, the seating of the stadium, you know? And the distance between the pillars is about a little over 8 meters, okay? So you can just get it out. So, and there's a fantastic person there named Roger Angel who developed these techniques for making these mirrors, and that's why that's there. It's because of a person, really, and then the team that he built up to make those mirrors. Okay, now, okay, so it doesn't look that big, and in fact, the effective area, since part of it's missing, so it's 8.4 meters diameter, but the effective area is only about 6.7 meters, okay, once you get rid of the middle part. So 6.7 meter, you know, full thing would be about the same. So that's not that big. So why is the LSST special? So, whoops. Okay, first reason is the field of view. That means how much of the sky we see at once in one exposure. And it's about 50 times the area of the full moon. And so this is a picture of our sensor plane, like it was a mock-up. She is Suzanne Jacoby was our head of communications and education, okay? And so this is what our sensor plane looks like. I'll get to how many pixels that is in a minute. And that would be the full moon landing on our focal plane. Okay? So for comparison, the Hubble Space Telescope, the field of view for that would be, imagine a window 1 millimeter by 1 millimeter. Okay, tiny little window. Hold that at arm's length and look through it. That's the patch of the sky that the Hubble Space Telescope sees. So absolutely tiny. Okay? And we're seeing this huge, huge region in comparison to that. Okay, so really big field of view is one thing. Another is the length of the survey. Most times, like with the Hubble Space Telescope, people will apply to get a certain number of orbits and a certain amount of time on it, but it's not going to be a long length of time. Whereas we're going to have one comprehensive survey for 10 years. So it is going to be optimized for where do we look at the sky at any particular time, depending on where the moon is and clouds and how many times have we already viewed a patch of the sky, et cetera. So it's a huge optimization problem that hasn't been fully optimized yet. Okay, more room for you, okay, to come help us get that more optimized. So the length of survey, 10 years. The fraction of the time spent observing. So not moving the telescope, not reading out the sensors, not sharing time with other projects. We're trying to get that as close to 100% as possible. So we just capture more and more photons, right? What we care about is those photons from those really far away galaxies. And this actually brings up one of the reasons that the telescope is short and stout. You might think back, you didn't really explain. I explained how it has like 3 mirrors and bounces back and forth to make it short, but why is it short? And it's basically because of the not wanting to spend much time moving the telescope, okay, or reading out the sensors. You'll see in a minute, I'll tell you that this is a 3.2 gigapixel camera, okay? And so the readout has been designed with multiple readouts around the edges, so a lot of readout going on parallel, that we can read out the whole thing in about 2 seconds. Okay, so to get 3.2 gigapixels worth of data off in 2 seconds is quite the feat. The exposures will be 2 15-second exposures back to back. Or we might make it 1 30-second. That's still a decision to be made. Okay, but about 30 seconds. Okay, so then you do 30-second exposure. Now we want to move to another patch of the sky. So we know that we need to move, like the telescope, from pointing here to whoosh, pointing to a new spot. And that telescope is massive. Okay, and so it has to move and settle, like boinga, 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 after it's moved, settle in about the readout time. Okay, or maybe we'll give it another second, but that's about it. So about 3 seconds to move and settle. And so you couldn't do that with a really long telescope, okay? But if you make it short and stout, then it's not going to do all those vibrations and it'll settle faster. So that's part of the reason that it's short and stout like that. Okay, so we're going to be very efficient. And then another reason, the transmission of light through the optical system, like the reflectivity of the mirror, the filters, the sensor sensitivity, et cetera, is all the best we can afford. Okay, so it's just like, how much money can we throw at it? And that's what we will get. I say transmission of light through the optics, but also not just transmission, but like reflection. So that when you saw the picture of the telescope building, there's where the dome is, and then a big support building. So once a year, we take that 8.4 meter mirror off the telescope, bring it down an elevator into that support part, and recode it. Okay, so the coating gets off and gets recoded because it'll start losing reflectivity over the course of the year. So we do that. So 3.2 gigapixel camera, I just said, or in megapixels, 3200. So we could ask, just how big is that image? So one way to ask would be, how many MacBook Retina displays, and I've got the specs here, okay, are required to display just one LSST image at full resolution? And how about, right now, I'll do what I do in class. We'll pause a minute. Think this through, talk to your neighbor. What's the answer? Go ahead. Got to get your brain working, okay? Got some numbers here. If you can't read it, let me know and I'll read it to you. It says 2880 by 1800. Order of magnitude. You don't need a calculator, just approximate. Okay. Yeah, so I don't use calculators. Yeah, so one way to look at it is, well, it's about 3K by 2K. Okay, but it's a little bit less than a 3K and a little bit less than 2K. So a little less than 3 times a little less than 2 is 5. Okay, so 5 megapixels, because we've got K times K. And then 3,200 megapixels divided by 5 megapixels is approximately 600 or so. Okay, so it would take about 600 MacBook Retina displays, so there they are, okay, to display a single image. And we do that every 30 seconds. Okay? So then I won't have you calculate it, but you can start thinking, oh my God, that's a lot of data coming off the telescope every night. Okay? And so it's about, it's tens of terabytes of data per night. And it's coming off a telescope on a mountaintop in Chile. Okay? So then you got to get it down the fiber optic system, down to a center in the closest town, La Serena. And that's actually where, do you remember there are earthquakes in Chile quite a bit, and this telescope is meant to withstand them. But there was a tsunami, do you remember, a year or two ago that hit the side of Chile, and it was right that town, actually, La Serena, or just south of it, that it hit. Kind of washed a bunch of the town away. So you get the data down there, and then you got to get back to the supercomputing center in Illinois, okay, which is where a lot of the processing will be done. Half of the data will also go to France to be processed there. So we're going to start spreading it around the world to be processed. And so when they were designing this, we had to think about a couple of decades in advance about the fiber optic system between Chile and the United States so that it would be ready to handle this data. And it's a not insignificant fraction of the total amount of data coming from Chile to the United States will be for this telescope, okay, the data coming off of it. Okay, so we've got these amazing images, and we have a lot of them. In fact, so many that every patch of the sky at the end of 10 years, we will have viewed about 1,000 times. Okay? And in 6 different filters, so 6 different parts of the spectrum, from the near ultraviolet to the near IR. So mostly in the visible, but a little bit into the both edges like that. Okay, so like I said before, we can do all these things with it, taking an inventory of the solar system, explore the transient optical sky, map the Milky Way, and probe dark energy and dark matter. And so now let me talk a little bit about my passion, which is the dark matter and dark energy. So I said earlier that dark energy, right, the Nobel Prize was given for it, that it was a discovery that space itself was expanding at an ever-increasing rate. Okay? So you can imagine space, like in this picture here, and embedded in space are these gravitationally attracting objects. We just have them as spheres here, equally spaced, but in our universe, these would be, well, we would say galaxies. But actually, the galaxies are hosted by what? What hosts a galaxy? So the galaxy is the actual stars and stuff, but most of the mass is in the form of dark matter. Okay? So about 90% of the mass of a galaxy is in the dark matter, and then the visible stuff that glows is only a small fraction of it. Okay? So these spheres then would represent basically the clumps of dark matter. And they are gravitationally attracting each other, right? All the dark matter. And so as space expands, and Einstein predicted that space will naturally expand or contract. Okay? And you may have heard that he thought when he first developed special relativity and found that the math was saying space can expand and contract, at that point everyone looking out there thought, no, space is not expanding or contracting. Things are not moving farther apart from each other. So I've got to stop this in the math. And he found that he could do it by adding a very simple term that we call the Einstein's cosmological constant. Okay? And it was a term that would stop this from happening. But then he found out, actually, or realized that it would stop it, but it was not a stable equilibrium. Remember what a stable and unstable equilibrium is, right? If it's stable, it means you perturb it a little in either direction, and it'll come back to that point. So for this, it would be that what we would be perturbing is density of the universe. So you could have exactly the right density with this cosmological constant, such that the slightest perturbation in density, if it was stable, it would bring it back to just the natural kind of density. And he realized afterwards, after he'd proposed this, that it was actually an unstable equilibrium. So the slightest little change in density of the matter in the universe would be a runaway process, and it would either start to expand, run away, or contract, run away. Okay? So it wasn't even a good solution. Okay? And sometimes you hear that Einstein called the cosmological constant his biggest blunder, and part of it is because it wasn't a stable solution. And that's a really good thing, right? In all your engineering classes and physics classes, you find like a maximum or minimum, and you have to figure out, is it a maximum or a minimum, right? It's not enough to say it's an extremum. Okay, so anyway, so space is expanding, but there's this gravitationally attracting stuff in it. So back in the like early 1990s, when people were doing experiments or proposing experiments to explore the rate at which the universe was expanding, the assumption was that the expansion of space was slowing down because of all this gravitationally attracting stuff embedded in space, kind of pulling it back from expanding. And so let's picture what this looks like, this expansion. And notice that we've got some rulers here, okay? And so rulers are anything that establish a scale for us in the universe. And as the universe expands, notice that the spheres are not changing in size and the rulers are not changing in size. They are just getting further apart, okay? So that's what the expansion of space means. Things are getting further apart because there's more space between them, but the objects themselves are not getting bigger. Okay? So the rulers are not getting bigger. And you can say, well, why not? Why is not the space not increasing there? And the reason basically is that what determines the length of a ruler is not gravity and general relativity, it's electricity and magnetism and quantum effects, okay, that really control how big atoms are and how big molecules are and how big solids are and things like that. So it's not general relativity. So the objects stay about the same size. Okay, so now you got the idea of what expansion of space is, and Hubble measured to within a factor of 10 okay, the rate at which space was expanding. And so people set out in the mid-1990s to use type 1a supernova, and I'm not going to go into that experiment, okay, but to measure the rate at which the expansion of the universe was slowing down, and instead they found that it wasn't slowing down, it was speeding up, okay? So the expansion of space was speeding up with time. And in fact, it had been speeding up with time, we figure, for about the last half of the age of the universe. It's been accelerating, the expansion. So you could ask, well, can you accommodate this in the math? And the answer is yes. Put the cosmological constant back, okay? Einstein's cosmological constant. Put it back in, and you can cause this slight expansion of the universe, okay? Or this accelerating expansion of the universe. And when you put that in the math, it has the effect of an energy density in the universe. So that for every unit volume, there's some density of energy. And it's constant. That's why it's a cosmological constant, okay? So constant energy density, you think, that's weird. Constant energy density, so per unit volume, the same amount of energy, but space is expanding, so there's more and more volume. So does that mean energy is not conserved? Yes, that means energy is not conserved, okay? So sometimes you learn things in one area of physics, and then you find when you go to a broader level of physics, what you learned no longer holds, okay? Like in classical mechanics, is there any limit to how fast something can go? No. But then you learn special relativity, and you say, nothing can travel faster than this number c, okay? Then in special relativity, energy is conserved, but then you go to general relativity, more general, where space can expand, and energy is no longer conserved, okay? So yeah, don't be surprised when these things like, oops, everything got knocked out from under me. Energy is not conserved, okay? With this, cosmological constant. Okay, so in the math, given what we were measuring for the expansion of space, it turns out about 70% of the energy density of the universe is in the form of this dark energy. The 30% is in the gravitationally attracting stuff, and of that, a little bit is ordinary matter. Most of it is this dark matter that gravitationally attracts, but is otherwise invisible. Okay, so it shouldn't be called dark. Something's dark, like my jacket, if it absorbs light. Dark matter doesn't absorb light, okay? It just doesn't interact electromagnetically at all. So how will the Large Synoptic Survey Telescope explore dark energy? We do it really using statistics. statistical type effects, okay? I remember the first statistics class I took as an engineering science student, and I really loved it, okay? It was like quantifying something we kind of have physical intuition for, and statistics has become more and more important. So I would say take as much statistics as you can, okay? You're going to be applying it in almost no matter what you do. So it's all kind of statistical. So what this is a picture of is what we call large-scale structure in the universe. This is the product of, not an observation, okay? This is a cosmological simulation, where we will start with, in our simulation, with almost uniformly distributed matter, mostly dark matter, basically. And then it's got some quantum fluctuations in it, so that some areas are a little bit overdense compared to others. And then let time go on. And wherever there's an overdensity, it'll start attracting more and more matter away from the intermediate areas. And that matter starts to form into, actually first kind of like almost like planes, and then filaments, and then where filaments can join, then clumps. And so these are clumps of dark matter. And I'll play the simulation. So it'll start off pretty smooth in terms of the density, and then end up about like this. And so these are clumps of dark matter that would then host galaxies. And you could also end up with galaxies being hosted along these filaments of dark matter as well. And of course, and now we'll play it forward in time. So it's starting off pretty uniform. It's starting to develop. And as the simulation is running, we're actually moving out, 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 looking at a wider and a bigger and bigger region of the universe, because space itself is expanding, okay, while this is happening. So stuff is coming together, but space is always expanding. So you know, from when the cosmic microwave background radiation started to stream through the universe to now, space has expanded by about a factor of about 1,100 in each direction, okay? So we need to like keep expanding out. And yeah, so all these clumps, you can see how they're gravitationally interacting. And it's a little hard to tell too, because they're all at different depths from us, you know? So it's like, wow, those don't seem to be impacting each other. It might be that they're very far apart in depth. So these cosmological simulations are incredibly important for interpreting what we see, okay? Because we can't, you know, we don't care in cosmology where any particular galaxy is. If you just gave us a whole bunch of, like, we call them postage stamps of pictures of galaxies, no information. We need to know where are they relative to each other, and what is the statistics of their relative positions, okay? How is it correlated? So it's correlation functions we care about. So we use the positions of billions of galaxies to map that cosmic web. So that was a dark matter simulation. Simulating the ordinary matter is really hard, okay? Dark matter just interacts gravitationally. Ordinary matter, electromagnetic interaction, weak interaction, strong interaction. Oh, and there are protons, and there are neutrons, and there are electrons, and there's chemistry, and you know, the whole thing. So it's really hard to do the simulations of the ordinary matter, but we're making progress on that as well. Okay, so I show this picture because we use the positions of billions of galaxies to map that cosmic web, very much like on that first slide. I was just showing you a picture of light, but you knew exactly what that was, and you could pick out cities, et cetera, because the light marked where the land was, the dark land. And so we're using the galaxies to mark where the dark matter is. And so we may end up with, for example, a simulated dark matter distribution that looks like this. And I should have mentioned that in these simulations, what we show as light is a high density of dark matter, okay? So the lighter it is, the more dark matter there is there in terms of density. Okay, so then we need to say, where would the galaxies go? That's a whole other area of physics and astrophysics, figuring out how do the galaxies occupy this dark matter. And so, for example, here's one, a predicted galaxy distribution to go with this simulation, okay? And so you can see that these galaxies are not uniformly distributed, right? And you'd say, well, how would I describe the non-uniform nature of those positions? And you would do it using something called two-point correlation functions. You may hear about three-point correlation functions. So if you hear about those things in statistics, pay attention, okay? That's how we can quantify what we can kind of see with our eyes, that this is not uniformly distributed. Okay, now we use the galaxies to say where's the dark matter, measure some statistics about that, learn it. But we're not actually seeing the dark matter. It's like seeing whoops, I didn't see that. Seeing the lights on the map, okay? That we're just seeing the light. So what we would like to do is have a more direct way of seeing the dark matter. And yeah, I'm going to skip that. So what we can do is use something called gravitational lensing to map the evolution of the dark matter. And this is where my research is focused, is this gravitational lensing. And when I decided that particle physics, I wanted to do something different, go over to cosmology, this is what really attracted me. Now, so here's a fine optical instrument. So rather than a telescope, I've just put an eyeball here, but it's pretty similar. Here's a galaxy off here. The galaxy emits light, so like a photon, and it enters your eye. And I just want to emphasize that we all remember that the way we figure out where that galaxy is from the direction of the photon, that the photon's traveling as it enters our eye. And our eye will reconstruct that for us, okay? So the direction as it enters our eye is very important, okay? We don't see the photon out here. All we see is what happened, the direction on impact. So now we're going to put in the middle here a cluster of galaxies. And galaxies cluster. They are housed or hosted by a clump of dark matter that I'm just representing by a sphere. So at this point you say, wow, that ray of light might not even make it through there. And more importantly, Einstein, when he was developing general relativity, predicted that just like regular matter is attracted by, gravitationally attracted by something with mass, so is light. It's easy. He would describe it more that matter, all that matter here, is affecting the shape of space itself. And so photon traveling in a straight line through this space is actually, we would see it as a curve because the space itself is curved. So a photon coming like this might start off going in that direction, but it'll be impacted by this. And a ray a certain distance away will be impacted such that it ends up entering our eye. And then we ask ourselves, where would we perceive that to be? And so where would we perceive the galaxy to be? Would it be here, or point with your fingers? Yes, up, like that, okay? So we would say, aha, there's a galaxy up there. And we'd actually see an image. It might be distorted, but we'll see an image of a galaxy. And we live in a three-dimensional world, not in a flat plane like this. Well, actually, even in the flat plane, there's another ray that could leave this and make it into our eye, right? And that would be one that goes down here, and therefore we would see another galaxy down there. Now, we live in a three-dimensional world, so what other light rays could leave this and get into our eye? Not just those two rays, but all the rays on a cone. Yeah. So basically, a cone of light coming out here will all be bent and make it into our eye. So there's a cone of light coming into our eye. So how do you perceive a cone of light? As a ring. Okay? And we call that an Einstein ring, because Einstein predicted that these rings are, in principle, there. He thought we would never detect them, okay? Never be able to detect them because it's such a subtle effect. But we can. And before I show you an image, let me just show you, you're wondering, what is this for? You might wonder, that kind of effect of turning a dot into a ring, is there a classical optical system we could design that would do that? In other words, is there a piece of glass, like a lens, that would image a dot into a ring? And yes, there is, but the lens would be, like if it's flat on one side, instead of being concave or convex, it needs to be concave, up towards the middle, okay? Just like the bottom of a wine glass. So if we took the bottom of a wine glass like this, and that would provide the same optical effect as gravitational lensing. So I have a sequence of pictures here that I took. I take my green graph paper that I've been using since engineering science, okay, for problem sets. And not the same green graph paper, but I still use that green graph paper. And put a dot on it. And then we'll hold the ring. And if you do this, okay, hold the lens about an inch or two off the paper. Don't put it down on the paper. Okay? You need the light to come up into this. And you'll see a ring. And look at the graph paper itself. Do you see how it's no longer this rectangular, rectilinear grid, but rather all these curves here? Okay, that's like the curved space, okay, that the mass would form. Okay, so you see the curving there. Now, it'll form a ring like that if the dot the lens, and your eye are all lined up on a line. If instead we move the lens to the side a little, you might wonder what's going to happen to a ring. It'll split, the ring will split into two arcs. Okay, so we see an arc over here and an arc over here. So you'll see multiple images then of the same galaxy, and they're distorted, right? They're turned into an arc like that. So then you could ask, well, do we really see arcs like that in the sky? And the answer is yes, and here's an example, okay? So this is the Hubble Space Telescope picture, and you see all these arcs here, and then you see these golden galaxies. The golden galaxies, these big blobby ones, that's a galaxy cluster, so a cluster of galaxies hosted by a huge amount of smoothly distributed dark matter, and then these curves are marking out what the dark matter distribution looks like. Okay, and so you can see how they're curving around something relatively smooth. So that kind of lensing, gravitational lensing, we call strong lensing. So strong versus weak. So strong lensing is stuff you can see with your eyes, like I showed right here. And it's due to very dense clumps of dark matter, and it's relatively rare. Okay? What we will be studying with the LSST, we'll do that, okay? And we'll see many, many examples like that. But every galaxy we look at, its image is being distorted subtly by the distribution of dark matter between where that galaxy was and us. And so it contains, all that smearing of the galaxy's images contains information about how the dark matter is distributed. So what my group works on is this very subtle weak lensing due to the entire distribution of dark matter that distorts the image of every galaxy by about 1 part in 1,000. By that, what I mean is that if a galaxy has a certain shape, and they're sort of elliptical in shape roughly, then depending on how the dark matter is distributed, in one direction it's going to be squashed and the other direction stretched by 1 part per 1,000. Okay? So there's no information in an individual galaxy because we didn't know what it looked like in the first place. Okay? But what you can do is if you could get like 10,000 galaxies all in one region of the sky, measure all their shapes and average them, then we can see that 1 part in 10,000 effect, assuming that the universe is isotropic and doesn't care about any direction. So we say, aha, everything's stretched slightly in that direction. You might think like, wow, 10,000 galaxies, and that's about the amount we need to get the statistical precision. That's a lot of galaxies. Fortunately, there are a lot of galaxies out in the universe. Okay, we will image about tens of billions of galaxies with LSST, and about a few billion will be useful for measuring this gravitational lensing. Okay, so 1 part per 1,000 means you have to care a lot about what we call systematic effects, and those effects that we have to understand to exquisite precision are things like the impact of the Earth's atmosphere. Okay, so my group does a lot of work on this. Okay? So it's all Kolmogorov turbulence, and so we end up learning a lot about turbulence, which is fun. We have to understand the telescope optics, the cameras, the sensors, everything. And just to put it in perspective, these photons have traveled billions of years to get to our galaxy and our telescope. And then in the last millisecond, all this stuff happens to them. Okay? They come into the Milky Way through our atmosphere, through our telescope, et cetera, and into the sensor, turn into an electron hole pair that we detect. Okay? So we have to understand that last millisecond in order to understand the first 10 billion years, okay, of their journey. Okay, so I'm going to wrap up with a couple of things here so we can have lots of time for Q&A. The teams who are building these are large. This is only a fraction of it. This was taken in 2012. This was called an all-hands meeting. This was about the telescope. And this little yellow box, that's me right there. Okay? This was in Tucson, where the mirrors was made. This is the LSST Dark Energy Science Collaboration, and we meet internationally sometimes, and this one was in Oxford. And do any of you know, in astronomy and astrophysics here, Renee Holzek? She's a relatively new professor here. Anyway, she's a member of the Dark Energy Science Collaboration, very active. Okay, so remember her first name, Renee, and then H-L-O, so Holzek, I think. So if you're interested in doing research with this, contact her, okay? And you might be able to get involved. Oh yeah, and I mentioned earlier too that with your 1-year thing, if you wanted to get involved in the telescope, we have a page. It's called LSST is Hiring. Okay, this is an older one, but we always have jobs coming up. So the Large Synoptic Survey Telescope is seeking scientific, engineering, education, and administrative talent to build one of the most important scientific experiments in human history, in double quotes. I don't know who said that, okay? But it really is this biggest census of the universe ever done. And it sees the diversity of its team as a critical component in constructing and operating a large scientific facility of value to all, so meaning internationally. Okay, so one last thing I want to touch on is how can we prepare you for what I call team science, working in teams, discussing problems, solving them together. One of them is by changing pedagogy. So I've been very active in changing how we teach. So changing pedagogy coupled with an inclusive culture. So these are two of my recent quantum mechanics classes that I teach. Okay, so I've got about 35 students in the class, and I do like maybe 5 to 10 minutes of lecturing just to introduce a concept, introduce the notation, etc. And then rather than having you watch me demonstrate how clearly I can derive all this, okay, instead you derive it. Okay, so these students are working together, and they've got some sheets, and there's a whiteboard there that they're working on. And and I explain to the students too, half of you won't finish the activity in the time that I'm going to give. But that's okay, because the point was, if you make it halfway through, you then have figured out what's the notation, right? What are those symbols? What do they mean? What was the question, right? Because sometimes someone's like deriving something on the board, and you're wondering, like, where did that start? I have no idea what they're doing. So what is the question? And you got started on it, okay? So you made your way through it enough that you're at that point saying, I could finish this on my own later, because you got the important parts, okay? And the rest often is math after that, and that's best to just struggle on your own anyway, kind of with that, or with other students, etc. And then I'll bring them back together, and again, half of them won't have finished, that's just fine, but then we discuss the result. And what does it mean? Let's take limiting cases, let's take some special cases, the thinking like a physicist part of it. So right now, almost all our physics majors, all their classes are taught, and engineering physics, they're all mixed together here, are taught in this kind of active learning way. And they really love it and call it deep learning, okay? Because they're doing it themselves. And I also run a set of dark energy schools. And this is common in forefront research, that we are constantly organizing schools. And school is basically, research is progressing so fast that everybody has to go back to school. And so there are faculty. So this is actually one of my graduate students here, Somya. And she's talking to Alan Heavens. He's a professor at Imperial College in the UK. And they're just like, he's clearly listening to her. Like, can you explain that to me? And so we hold these dark energy schools. This is one of the teachers. I often recruit junior people, like postdocs, she's a second postdoc teaching there. And here she is, and we use these engaged learning techniques in this as well. And it's interesting because some of our colleagues from Europe now describe how much they like this, and they say, I really like this American way of teaching. And everyone's looking at them, no, this is not an American way. This is just what a few people are doing, okay? So if you get engaged in education, be willing to do something different, okay? I think people often are reluctant to, because they're like, well, I know that passive teaching doesn't work, but everybody does it, so no one's going to blame me for it. Whereas it can take courage to do something different. And my recommendation is, it's worth doing it, okay? Just do it. And if people say, no, someone tried that before, it doesn't work, don't listen, okay? And contact me, and I'll help you, okay? We've written some quick guides to active learning and things like this. Or if you have a faculty member, a professor who you think would be receptive, have them contact me and I'll get them started. Okay, so just to summarize then, I didn't read the proverb at the beginning, but if you want to go fast, go alone. If you want to go far, go together in a team like this. There is an important role for both in science and engineering. So I'm not saying that team science is the only way, but an increasingly important role for going together exists now in science. Okay, thank you. Okay, so we have about 25 minutes, up to 25 minutes for questions, if you have questions. So, less than 10? Yeah, okay, so we have less than 10. Okay. Yeah, for some reason I thought it was an hour and a half total, but yes. Yeah, go ahead. Yeah.
My name is Aiden, by the way, and I wanted to ask you, so basically, you said that, so about those, so when you were working on this team of scientists, were there any like sort of conflicts or like sort of like times when the like team couldn't decide how to move forward, and like how did you guys end up solving this? I know it sounds a bit cliche,
Right.
like it's because like everybody is like from like a different field, but like so it can be like hard to put all of it.
Okay, so the question was whether with such a big team, people from many different fields, for example, or different technical backgrounds, whatever, are there ever conflicts, and how do we make our way through them? One of the things is we try to set up a collaboration so that there's a way that either avoid conflicts or have a way to deal with them. So we do have things like code of conduct about how do you conduct yourself in meetings, et cetera, and just being respectful and listening to each other. The other is actually in the dark energy science collaboration, what I've been really impressed with is how a lot of respect and recognition of junior scientists. So we don't say young, we just say junior, okay? And junior is graduate students, postdocs, and people in non-permanent positions, okay? So like an assistant professor or something like that. And making sure that they have, lots of opportunities to take leadership roles, et cetera. And I think by doing that and having everyone play a major role, everyone is willing to pull together more. Because everyone is a leader then, kind of like, okay, we got to do this together, rather than just a few leaders kind of dictating what everyone else is going to do. Now the project side, that means like the construction of the telescope, that has to be much more kind of schedule driven. And there, we sometimes do have technical problems, really severe technical problems. Then you put together a team, it's going to figure out, diagnose the problem, how are we going to fix it, what's the impact on the schedule and the budget, keep our funders in the loop on this, how much contingency are we going to be using up. So it really is like a big engineering project to do that. But so I think it's just having good leadership too that sets an example. Okay, if the leaders at the top set a good example about collaboration stuff, that goes a long way. Okay, so if you have bad leadership, you got to solve that problem. So, yeah.
Hi, Professor. My name is Valentin. I do have two questions. One I want to ask you. So, my first question is, as a researcher, how do you do something significant? So, at this point of your academic career, I'm guessing that you've decided on your main direction of research. So, I'm more curious to understand, how did you come to this direction in the first place? Why do you think that this is the most promising direction for you to understand the universe, and there's something significant to be done here?
Right. Okay. Yeah. So how about if I answer that first? Yeah. So how did I find or find and choose this particular direction, and how does one make an impact also kind of like as an individual? So I think it's really important that you find out where you want to work and in what kind of situation. Because sometimes people want to work on what's called tabletop science, where it can all fit on a table. And so for physics, that would be, for example, atomic, molecular, and optical physics, or now sometimes called quantum science and engineering, where you got like a mushroom farm of optics and lasers and everything. And that will be a small team. There's other things like the ones that I mentioned at the beginning, huge teams of necessity. I would say find the size of team that you're comfortable with. And for me, I like the culture of the really big collaborations. To me, it's not a negative at all. And it's an opportunity to have these very international collaborations, which I love. So it's really finding what you like. I'd say the other thing besides, is it small science or big science, is are you a reductionist at heart? Do you like understanding things, like reducing them down, like in particle physics? Or describing the universe as like what fraction is these three things, rather than playing with an individual galaxy, okay? Or do you like complexity? Okay, complexity I would say is more like material science and solid state physics and things like this, where like you got the basic laws of physics, and now you're going to have Avogadro's numbers worth of them, like 10 to the 23, interacting with each other, and therefore you need statistical mechanics. If you haven't taken statistical mechanics yet, that's what you learn there, is how do you have 10 to the 23 particles, interacting, and out comes things like heat and all that stuff, okay? So do you like that, So figuring out for yourself what you like, and then you're mostly probably going to be happy there. And also, are you happy contributing to a team, and that's the accomplishment, or an individual? Within a team, like how does my group make an impact? I pick, I said like this 1 part per 1,000 kind of effect we need to measure with gravitational lensing. I love that, where we got to understand things in excruciating detail. I like that, okay? So that we can get this fundamental physics out. So it's finding what your taste is, and then you'll be happy. Should we do one more?
Yep.
Okay? Yes?
My name is Rufai. I know you said this statistics is very important in physics, right?
Yes.
Curious,
Yeah.
What type of, can you think a little more in depth on what that means? And do you use more advanced data science techniques to also analyze the data?
Right, yeah. Okay, so the question was, I'd mentioned that statistics are really important. Take statistics. A little bit more about what I mean, and is data science or machine learning, say? Yes, all of the above, okay? So data science, I view a lot of that is like dealing with big data, which is obviously really important there. Statistics, get a good foundation in the real fundamentals of statistics, and then just start taking some more advanced statistics if you can. Machine learning and AI, yes. The graduate student that I pointed to, Soumya, who was talking to the professor there, what she's working on right now is that we are going to see so deeply into the universe. We're going to look back about 3/4 of the way to the Big Bang. And because our images of our galaxies are all smeared out a bit by the atmosphere, the image is a little bigger than the galaxy would actually be. Because of that, almost every image of a galaxy is slightly overlapping with another galaxy. Okay? That's the density. That's how we get 20 billion in a picture in our whole survey. So we have been using kind of classical statistical techniques with our 6 bands, our 6 different channels of wavelengths to try to disentangle, is this 2 galaxies, is this 1 galaxy, et cetera. So Soumya, for example, is one of others that are working on this too, trying to use machine learning to do that. And so then you need really good simulations, okay, and then train your networks. And I love that she's doing that because it forces me to learn some of this, AI and machine learning. Great. I like, again, being on that learning curve. So yeah, all these modern techniques are very applicable in this experiment, and we're going to depend on that. Yeah. Let me see if someone else has a question first. Yeah.
Hi. You mentioned that each image that the LSSD will take will be about however many terabytes in size. I was just wondering what kind of technology it will be stored and post-processed.
Right. Okay. The storage, I'm not so sure, but the processing will be happening at the Illinois Superconducting Center. And in terms of the types of processors, it's a moving target. And what we're realizing, we have to keep up with, we can't define now how 10 years from now we would be processing this data. Because if you tried to predict 10 years ago the fastest processing now, that just wouldn't work. So parallel processing, et cetera. Yeah. Can I take one more? Because there was one student at the back who had her hand up. I'll do one really quickly, at the very back corner. Oh, okay, yeah, great. So good questions. How do I balance work life and family? So I have 2 kids. Maybe I should have mentioned that, but they're 27 and 30. And I had my children when I felt it was right for me. And I used that as like, if people said, no, you shouldn't have your first baby when you're an assistant professor, I was an assistant professor, okay? Because I just thought, if that doesn't work, then that means that's a problem with the job, not with me, okay? And so I tended to do things when I wanted to. The other thing is, some people have said, for all of you, choose your partner well. Okay, my husband's here actually, not here in this room, but he's here on this trip. And he does like close to 100% of the cooking, but I do the bills. So really you really do need, if you're going to have a family, have someone who's going to help you carry that load and get help when you need it. Okay, so I would say that. But the benefit of, I'd say, having kids was that at 5 o'clock I had to leave because daycare was going to close. And so it made me actually stop working at some time. Now, I just kind of work all the time, but I love what I do, so it's okay. Okay,
Thank you, Professor Burchat.
thank you.